All right, so we'll get started here. These slides, they say week 7. I guess they're technically week 6 and 7. We'll start them today and then kind of finish through next week. I have the short answer portions graded. I dropped off the multiple choice to go through the scanner, but I still haven't gotten them as of right now. So we will bother some people after class today to try to get those in. So you might see the exam scores pop up this weekend. At the very latest, they'll be up sometime on Monday. And it kind of depends on when I get them back from the scanner. But short answer part looks pretty good. I don't know. I was encouraged to see some of the scores that came through on there. We will kind of pick up where we left off on the exam, and we'll keep talking about continuous random variables. I think I got everybody's Excel graded as well, so you should see those scores up on Canvas. Any questions from me before we jump into things? So I'll mention one other issue, and I tried to look it over and it looked like there was no issues with this class. One of my other sections, the connect, all of a sudden just randomly synced like a quarter of the people's scores to scores that they weren't. So I don't know why that happened. So just in case, if that does happen where your connect grades change for any reason, it was not me. I should not be going in and doing that. So let me know if for some reason, all of a sudden you have a 0 for one of the connects. I have no idea what happened to the other section, so I'm now worried about all my sections. But so I mentioned that on the top. So continuous random variables, right? We said were these experiments that have an outcome. The problem is, right, we have an infinite number of possible values we could see. So the probability of any one value we said was what? I have an infinite number of possible values I could see. Approximately 0. Pretty much 0, right? And the limit is 0. Okay. So we had to look over different intervals and we could find the probability over different intervals. Now, the only one that we looked at was the uniform distribution, where everything was equally as likely. In practice, it's not very likely that everything is going to be equally as likely. So we've got this guy Gauss. He was really smart, did a bunch of different stuff. He was a Renaissance man back in the day. And him someone else discovered what we have now called the normal distribution. So it's also sometimes called the Gaussian distribution, or you might have heard it referred to as a bell curve. So all kind of names for the same thing. So I don't know, just kind of lead us into things here. Apparently he was brilliant. So when he was a kid, he was misbehaving and the teacher told him, go to the corner, add up all the numbers from 1 to 100, thought it would take him a while, kind of keep him occupied. Right, so 1 + 2 is 3, + 3 is 6, + 4 is 10, right, all the way up to 100. Comes back in a matter of minutes with the answer, right, or 7 minutes, seconds here, right? So how could maybe you add up the numbers from 1 to 100 very quickly? So what's 1 + 100? 101. What's 2 + 99? 101. What's 3 + 98? 101. Basically, you've got 50 pairs that add up to 101. So 101 times 50 is just 5,000 + 50. Right? So he was very young, could realize this, right? He has a different kind of brain. And also, it's kind of interesting to think about things like that. There's actually a formula if you want to add up from 1 to any number. This formula would actually give you the correct answer. Just kind of interesting. I mean, I don't know when you would ever apply that. We're not necessarily going to use that, but it is kind of an interesting kind of thing that comes out of the story. So he's really smart, right? What we really care about is that he came up with this normal distribution. Right? The normal distribution is interesting because we see it pop up everywhere. Like a lot of bio, like you're all in the business school, but if you have any interest in like biology or kind of human performance, all these different biology metrics like height, weight tend to follow a normal distribution, right? IQ, right? Different measures of aptitude always tend to follow this normal distribution. So you've got this normal distribution that describes a lot of different continuous random variables. It's not just like we came up with it. We see it happen in nature a lot. Okay? So I've got a couple examples. Oh, rainfall, right? A lot of times when you get rainfall or temperature, things like that, they tend to follow a pretty nice normal distribution as well. And this is all kind of laid out in this book. I mean, you can go down like a YouTube rabbit hole if you really want to, and just like all the different things that are the normal distribution, how it pops up, how it's related to, what's that, the golden ratio or whatever that we see happen. So, it, if you're real nerdy and you want to do that, like Google search normal distribution and you can provide some interesting stuff. Right? So we're starting here, but eventually by the end of this course, we're going to get to regression. But all of regression kind of hinges on the fact that we understand what's going on with this normal distribution. Okay? So the probability density function looks something like this. Don't write this down. We don't have to use this. I mean, we could, but it would make this class a lot harder. All right, so ultimately what we're going to have this equation. And if we use this equation, we could graph out that normal distribution, right? So just like, if I had y is equal to 10 plus 4x, I could draw a line. That's what I'm doing here. I'm graphing out this equation, this formula. Now you'll notice it hinges on two things, okay? We've talked about this a little bit before, right? And I've kind of drawn you a similar example in the past. So notice E and pi, those numbers aren't going to change. But depending on the variable we're looking at, right, it could be a different type of normal distribution. So we have height and rainfall both follow normal distribution, but we know they don't have the same mean, right? I mean, height is measured in inches, so is rainfall, but the average rainfall is going to be like, way below 10, and the average height is going to be, above 50. So the things that the normal distribution defines it are going to be its variance and its mean, right? The mean tells us kind of where we're drawing this normal distribution, right? Shifting along the x-axis. That variance should tell us what? Remember what we said about the shape of a distribution. If the variance gets higher, what happens to the distribution? So a higher variance means there's more variation. So actually a higher variance would flatten out that distribution. So we've already talked about kind of how that mean and variance define distributions, and it's the same thing here with the normal, right? That mean shifts it, right, along the x-axis, and the variance kind of flattens or makes it more peaked, okay? So ultimately what we could start doing is something like this. Let's say I've got, height's an easy one, just so I can do the numbers off the top of my head. So let's say we're looking at the distribution of height. It looks like it's a nice normal distribution. We've got the mean, I don't know, is we'll say 68 here. So what I could do is something like, okay, well, given that this is the average height, what is the probability that if I chose someone at random, what's the probability that they're in between, I don't know, 60 and 64? Well, the probability that we see a height in between 60 and 64 is kind of reflected by whatever the probabilities associated with those values are. Now, this is where it gets kind of weird because the probability of any one value is 0, but over a given interval, we know it's more likely we see values between, say, 67 and 70 than seeing values between 60 and 64, right? Because those are further from the mean. And this formula, this PDF, this probability density function, tells us what those probabilities are. Okay? So what we could do is integrate, right, from 60 to 64, integrate that function. It tells us the area under the curve. But like, let's try to not do calculus, right? If we can avoid it. So we'll have a way that we can look that up. Eventually, we have to talk about a little bit more things before we get there. But someone's basically already done all this integration for us. Okay? But if we really wanted to, we could plug our mean in, plug our variance in, and then do this integration between whatever two values we were interested in. So one thing that you'll see up on Canvas, and it should just be under the Files tab, is this standard normal table. Okay, so we'll go over how we use it here in a second, but basically this table is going to be that integration that's already been done for us. Okay, so I would suggest whatever you bring to class, if you have a computer and you don't care having it pulled up on your computer, that's fine. If you don't, I would print this out and bring it to class because we're going to start using it in class for iClicker questions and things like that. Okay. Let's go back here. Any questions up to this point? Just haven't really done anything too crazy. Today shouldn't be too bad. So right? It's, you know, going to have some nice properties. So this normal distribution, notice I'm trying to draw it so that it looks symmetric, right? It looks like each time I draw it, I can fold it in half around that mean. And if it's symmetric, what ends up being true is that mean is equal to the median and it's equal to the mode, right? It's not skewed in either direction. We already talked about it's defined by the mean and the variance, right? And that'll just kind of play out as we work through some of these problems. So the mean can be any real number. So we already talked about, right? If it changes, that's just going to shift our normal distribution around or kind of along the x-axis. And then if we have different variances, this is where we said the higher the variance, kind of the flatter this is going to be, right? So seeing values that are further from that mean, when I have a really low variance, those probably start to get higher. And this isn't a perfect drawing, but you can, you know, kind of can see that it's getting squished down or flatter as the variance gets higher. So with this idea in mind, right, we could start to look at things like human height, and notice this is like, I mean, pretty perfect normal distribution. Maybe there's a little skew to the male height. But notice if we're comparing those, the mean height for males is a little bit higher, right? So it shifts that to the right. What must be true about the variance in male and female height given this drawing?
The variance in male height is higher.
Yeah, there's a lot more variation in male height. That's why it's a little bit flatter. So, you know, you can think about, what was I going to say? Oh, so this actually ends up, it's kind of interesting when we look at biological markers a lot of time. For whatever reason, males are just unstable, so they typically have like a wider variance. I say unstable, I don't know, like mentally. I mean, like just whatever reason, they're like on the height and weight, all these things. There's a much wider variance for males than for females. For most variables you can think of. So it's kind of a nice visual of it. I think it makes sense with human height, thinking about the mean shifting it and the variance kind of flattening it. Right? So we have this normal distribution. What has to be true is, well, I didn't want to show this one. The area under the curve is always going to be 1, right? Just like with the uniform distribution, but our curve was like a flat line, we're still saying, well, if I took the probability of every single possible infinitesimally small interval and I added them all up, right? Well, that's just every single outcome I can ever see. So those probabilities should add up to 1. Or said differently, if I went from negative infinity to infinity, I integrated this function, right? The area under that curve should be 1. Also, never say I'm not nice. See, I'll let someone stay after and take their exam. So I'm trying to build a reputation. Hopefully not that I'm like a pushover, but hopefully that, you know, I'm not the meanest person. So kind of an interesting thing that happens with this normal distribution is no matter what the mean and the standard deviation are, if you go out 1 standard deviation above and 1 standard deviation below the mean, you're always guaranteed that if it's a normally distributed variable, there's a 68% chance that you see a value in between 1 standard deviation above and 1 standard deviation below. We'll eventually kind of be able to prove this to you using that table, but for now, kind of taking at my word. If we go out 2 standard deviations, you know that there's always going to be 95% in between 2 standard deviations above and below. You don't have to have these values memorized. We'll start kind of, you know, I'm just going to show you how to find them eventually. And then 3 standard deviations, we've got almost 100%, right? 99.7. So if you go 3 standard deviations above and below the mean, the probability you see something in that range is almost 100%, right? Very, very close. So the idea is, you know, why is this true, right? Well, partially it's true because we haven't put any values in for that mean and that standard deviation yet, right? So as long as it follows a normal distribution, it doesn't matter what the mean and standard deviation are. If we go a certain number of standard deviations to the left and the right, we know what that percent in between would be. So eventually build up to be able to solve this for ourselves. What's that mistake here? Oh, you guys probably haven't got to this point yet because you're sophomores or a couple of freshmen. So in maybe some of your upper level courses, or we might start here, some of your professors talk about things like 6 sigma, right? So this is the idea that if I'm at 3 sigma, right, the probability that I'm, you know, if I go 3 sigmas or 3 standard deviations above and below, I'm already at 99.7%. So if I go 6 sigmas, I'm at like 99.9999%, right? So I can almost like guarantee if I go 6 sigmas out, you know, and I know I'm going to see something in that range, right? We're almost with a 100% guarantee. That's a little bit lower. That's like 99.999, but still, right? That's why we go out 6 sigmas. Probably 3 would be more than enough, honestly. We're very close. Okay. So it's defined by the mean and the variance. So we typically write out, I've got this normally distributed variable x, right? So it's normally distributed with a mean of whatever the mean is and a variance of whatever the variance is. So in practice, we're going to write out those numbers, right? Just kind of x is distributed normally with a mean of 20 and a variance of 30. I will write those numbers in. Okay. So we have a special case, right? Which is the standard normal distribution. Okay? So a standard normal distribution, the reason why it's called standard, it's like we've standardized the data. Right? So a standard normal distribution has a mean of 0 and a variance of 1. And what ends up being kind of unique is if the variance is 1, what's the standard deviation? Yeah, the square root of 1 is also 1. So it's kind of the standard normal distribution has this nice property that the mean and the variance, sorry, the mean and the variance. The variance and the standard deviation are the same, and the mean is always 0. You can also imagine if I have a mean of 0 and variance of 1, if I go back to this somewhere, back further I thought. We go back to that probability density function. Well, if I plug in a 1 here, that kind of makes this a little bit easier to deal with. 1 here makes that a little bit easier. If I put a 0 in here, I'm just squaring the actualized values. So the integration of this function becomes a little bit easier if we can get a standard normal distribution. So it ends up being true. And also I know that Eli's not here, he was going to watch this, so I apologize for giving him a stroke right now, probably. But what ends up being true is we can convert any normal distribution into a standard normal distribution, which then, if I can convert any normal distribution into a standard normal distribution, and someone's already done the integration for all the possible values for a standard normal distribution, then I can use that integration that someone's already done, which is what's shown to us in that standard normal or that Z table that I showed you earlier. Okay? So if we can get our mean to be 0 and our variance of 1, our life becomes a little bit easier. And we're going to say that the standard normal distribution, instead of now calling it like X, right, we're going to call the variable kind of Z, right? So any value that we're looking at for a standard normal distribution, we will say that represents a Z value. Okay? So if I had a standard normal distribution, right, any of the values I'm thinking about, I'm going to call those Z values. Okay? Now, what those Z values represent is going to be the number of standard deviations away from the mean that that value is. So I'll try to give you, I think this is a good visual over here. So let's keep using that height example. It's normally distributed. We'll say the mean is 68, and I don't know, the standard deviation will make it easy as 6. Well, we can convert this. We can convert all these different values for height into Z values, right? For instance, if I thought about 74, how many standard deviations away from the mean would 74 be? 1. So that would actually represent a Z-score of 1. Right? Z-scores just represent the number of standard deviations away certain X values are from the mean. What's the Z value of the mean always going to be? Yeah, right? It's 0 standard deviations away from the mean. So we could kind of like convert all of these into a standard normal distribution by converting all of our X values into Z values. So then the next question is, well, how do I do that? How do I convert these X values into this Z value so that I'm just representing them with how many standard deviations away from the mean that value is? So, I have it in here. There we go. This is the equation that we're going to use. Right? So when we say a standard normal distribution, right, I'm essentially thinking about it as though I'm standardizing the data. So all I'm going to do is subtract the mean and divide by the standard deviation. So why does this guarantee that I'm always going to have, or why does this process kind of make my z-scores reflect the number of standard deviations away? Well, I'll give you a small example and we can kind of see it, at least it plays out. So 2, 4, 6, 8. Try to do an easy one here. So if I add these up, divide by 4, I get that the mean for this x variable is what? 20 over 4, 5. Right? So if I subtract 5 from each one of these original x values, right? So it'll be kind of like my, we haven't gotten our z-score yet. So 2 minus 5 is -3. 4 minus 5, -1. 6 minus 5 is 1. 8 minus 5 is 3. Now, if I think about what's the mean for that deviation from the mean, right? For this new variable that I created. Well, if I add these up and divide by 4, I get 0. So subtracting the mean from every single value automatically makes your new variable have a mean of 0. Okay? If you then divide by the standard deviation, right? So our standard deviation would be what here? So we'd have 3 squared, which is 9, plus 1 squared, so 10, 10. So I've got 20. This is a nice and easy one, I believe. The variance, I'll have 20 over 4 as well. Right? If I treat this like population data, which, right, we've got population standard deviation written up there. So if I divide everything by not the variance, but the standard deviation, right? So my standard deviation is the square root of 5. I'd end up with something like this. If I then take the deviation of each one of these values, right, from that mean of 0, well, that's easy to do, right? Subtracting 0 isn't going to change anything, and then square them, and then add them all up and divide by the number of numbers I have. So here, this would be what? 9 over 5, 1 over 5, 1 over 5, 9 over 5. So I add these all up, I get what? 20 over 5, which is 4, but I still need to divide by the number of observations I had. So divide that by 4, and my z-score ends up with that variance or standard deviation of 1. So by dividing by that standard deviation, it's always going to guarantee that our new variance and our new standard deviation will be equal to 1. So you can kind of see it play out with the numbers here, so you don't have to take my word for it. But it kind of makes sense. Like when you subtract the mean, it's almost like you're shifting that distribution back to 0. And when you divide by the standard deviation, it's almost like you're trying to kind of account for all the variation that exists in the data. So this z-score is going to represent the number of standard deviations away our different x values are from the mean. Right? So if we had a z-score of 3, right, that means that the value was 3 standard deviations above the mean. If we have a z-score of -2, that means it was 2 standard deviations below the mean. So the sign tells us whether or not we're above or below the mean. The number tells us how far away, right? Doesn't tell us the direction. That's the sign that tells us the direction, but the number tells us how many standard deviations away. So these z-scores are going to be kind of the standard normally distributed, right? Mean of 0, variance of 1, as long as we converted a variable that was originally normally distributed, right? Has to start out with a variable that's just normally distributed. We can then convert it into a standard normal distribution. So I always kind of like this little graphic as well, which kind of shows you can map out different values for x to their z-score. So if it's 3 standard deviations above the mean, that's always going to be a z-score of 3. 1 standard deviation below the mean is always going to have a z-score of -1. You can kind of see that play out if we look at our z-score formula. So we take the x value, subtract the mean, divided by the standard deviation. Well, what if that x value, right? Actually, I'll just erase it and say, what if we had something that was 1.5 standard deviations below the mean? Right? We don't even have to put the actual number in there. We can just say, what if the number that we're looking at is 1.5 standard deviations below the mean? Well, that's the mean minus 1.5 standard deviations. Notice the mean minus the mean cancels. Standard deviations cancel. So if I'm looking at something 1.5 standard deviations below the mean, I'm always going to end up with that z-score of negative 1.5. Any questions already? Sure. So I want to make sure we have like a real good understanding. We're going to use this normal distribution a lot. Okay, so why the hell are we doing this? Right? Why, well, I kind of already described, like, well, someone's already done the integration for us. It's a little bit easier when it's a standard normal distribution. So what we can do is think about, I'm probably going to want the probability I'm in between two values. And like that Excel homework, right? We did that with discrete random variables already, where we use that binom.dist, and then you made it cumulative, so you can find the probability that it was less than or equal to 15, and then the probability it was less than or equal to 10. Subtract this one from the large one, you're kind of left with just what's in between. So this is the idea that maybe cumulative density functions would help us here, because I could find the probability that something is less than B, then I could use it to find the probability something is less than A. Subtract that smaller one from the larger one, and I'd be left with just the area in between. Now the problem is the probability density function is complicated enough, right? The cumulative density function gets even more complicated. Well, other people have done the work, right? So we have these standard normal distribution, or we're often referred to as the Z tables, right? Where people have already done the integration for a standard normal distribution. So if I can convert my original X variable, those original A and B values I'm interested in, convert those A and B values into z-scores, I can look those up in the table, and it will give me the cumulative density, right, or the area to the left. So for instance, if I have a z-score, or I have some value that ends up with a z-score of negative 1.29, so it was 1.29 standard deviations below the mean. If I look that up in the table, it will tell me the probability I see a z-score of negative 1.29 or anything further from the mean, right, or anything below. So that table works as like a cumulative density function. And I'll show you how to look up in a second. Yeah, it's a cumulative density function, so it's going to help us kind of find some of these different. So here's the table, right? It's kind of small up here. So I said in the future, like printing it out so you can have it in front of you is going to be helpful. But basically, we've got our row headings represent the first decimal of our z-score. So if I wanted negative 1.29, and I want to know, well, what's the probability I see something to the left of that negative 1.29, right? What's the area under that curve? I look up negative 1.2, right? So negative 1.2 is that first decimal. And then my column headings are whatever the second decimal is. So notice 0.00 would just mean negative 1.2. 0.01, negative 1.21. 0.02, negative 1.22, right? I'm kind of like, I add my column heading to the row heading that gives me what number I'm looking for. So negative 1.29, all the way over here in the last column, 0.0985. So I just kind of find my first and second decimal, right? Go to where those two meet, and the table tells me the probability of seeing anything to the left of that value. So I think here I've got some little graphics too. There minus here, we've got our 10th place for whatever z-score we're interested in, our 100th place. We go down to where those meet, and that gives us the probability of seeing that z-score or anything below it. Which ultimately is like saying, well, what's the probability I see something that's more than 1.29 standard deviations below the mean? That's really what we're saying there. We're looking for that area to the left. Now, if this is a symmetric distribution, and I ask you, what's the probability? Let me make this one a little bit hard to think about. what's the probability you see something 1.29 standard deviations above the mean or anything below that, right? So you want kind of the area to the left here. How could you maybe find that? Yeah.
I'm just gonna take a guess. Is it like 1 minus 0.098?
Close, right? Oh, wait, sorry. No. Correct. Perfect. Yeah, I was thinking of the wrong number. Yeah, right. So this area over here, you automatically know because this is a symmetric distribution, but that's going to also be 0.0985. Now you can look 1.29 up in the table. I don't have it up on the screen here yet, right? So these are our negative values. Our positive values are going to be like on the other side of our standard normal table. But then if you know the area to the right, and you got that because it's a symmetric distribution, then you know the area to the left of that value just has to be 1 minus that. Sorry, when you first said, I thought you said like 0.9 or so. I was like, I know. But our 1 minus 0.9. So, you know, we can use this idea that it's a symmetric distribution to help us, and we can also use this complement rule. That's really all we're doing here, right? We know that the probability I'm 1.29 standard deviations above the mean, and the probability that I'm 1.29 or standard deviations or below that, that's every single possible value I could see. Those two things are complement. They have to add up to 1. So we're like hidden in behind there. What we just did really is the complement rule as well. Any questions on why that works? Yeah.
I'm still just kind of how you figured out which like column to go into with the from 0 to 9.
Yeah, so.
Just because 9's the last number.
Yes. So basically our column headings are going to be whatever is in the, it's not, oh, here we go. Whatever's in that hundreds place, or whatever's the second decimal, right? So we'll look up our first, so let's say I had 2.36, right? Or negative 2.36. Negative 2.3, that goes to that first decimal. And then it was negative 2.36, so I just go over to the column that has 0.06, right? Whatever is that second decimal. That clarify? Okay. So yeah, so we've also got the positive values. Kind of already mentioned, if I looked up 1.29, I should get what? 0.9015. I'm doing this math in my head correctly. We can, hopefully that's what we get when we look it up, right? So 1.2 all the way over to 9. Did I skip a row? Yes. 1.29. Sure enough, 0.9015. Okay. We looked up that 1.29. And we found that 0.9015. Now, as I just demonstrated, especially if you aren't doing it very carefully, it's easy when you're using this table to accidentally go up or down a row on accident. So one thing that I've seen people do that I think is pretty helpful is like have another piece of paper, and that way like you can kind of like hold it down there so you make sure like you're on the right row. Just that's in practice probably the easier way to do it, because yeah, it's very easy to make that mistake, especially until we're like really used to the numbers we're seeing here. Because over time, as you work through more and more examples, we're going to be seeing like the same values pop up a lot. So notice this 0.9015, that's really close. In fact, I think it's like about, in between these two, these are as close as we can get to about 90%. So really what this is saying is if I go 1.29 standard deviations above the mean, I can guarantee that 90% of the outcomes that I'll see are below 1.29 standard deviations above the mean. Excuse me. So that kind of, saying that a different way, only 10% of the observations will be even further from the mean, at least above it. So we'll see these benchmark values pop up quite a bit. So 1.29 will be a z-score we see a lot of, 1.65, 1.98. Yeah, so it's 97.5. And then 2.57 is another one we'll see happen a lot. But this is just going to come out of more and more practice. So we kind of already talked about this idea, right? We can kind of use this complement rule in the background to find the probability of being below certain values, but also then the probability of being above, right? So if I wanted the probability of being above 1.29 here, we'll just do 1 minus 0.9015. So here are those values. Oh, it's 1.96. I was a little off. But here's kind of those z-scores that we'll see pop up a lot. Okay. And that's because you can kind of see they're nice like little cutoff percentages. 90% of the data, 95, 97.5, 99, 99.5. If we're only going out to 2 decimals, this is as close as we can get. Right? If we go out to like 3 or 4 decimals for these z-scores, we can get even closer to benchmark values. So we've already used this idea, talking about it symmetric. Another thing that kind of helps once we get to exams and questions, what's the probability that you see something to the left or the right of the mean? It's symmetric, right? 0.5 on each side. So a lot of the times we can like, what's going to be true about every negative z-score? The area to the left of it should be, yeah, if I'm looking at negative z-scores, the area to the left has to be less than 0.5, right? If I'm looking at positive z-scores, the area to the left has to be greater than 0.5, right? So if I look back at the table I was showing you, notice for the positive z-scores, all these values are above 0.5. In fact, if you look up 0, right here, 0, 0, 0.5, right? And then if you look at the negative values, these are all less than 0.5. So that kind of makes sense with our visual. Okay. So where were we? Talk about this symmetric. Oh, so this is my justification. I put this slide in to tell you. This is why I'm telling you to print it out, because even if I try to show it to you before I ask you an accurate question, I can barely read this standing a couple feet away. Right, this is ridiculous. So having that in front of you is going to be kind of crucial moving forward. Right, starting next week. So starting on Monday, I'll expect that you have this with you. I'm not going to use eye clickers today, but let's think through these. Right. So I want the probability that z is greater than or equal to negative 2.53. I think this is one I can solve without actually looking it up. Yeah. So why can I solve this without even really looking it up in that table? And then I'll show you how we look it up in the table. But we start working with this normal distribution and the standard normal distribution. Drawing things out is really helpful. So I just gave an exam in 201, and I watched some people take the exam and they don't write anything down, and I'm just like, I don't understand how you think this is going to go well. Like having a picture in economics, and honestly, having a picture in statistics almost always makes it easier to visualize, right? Makes it easier to think about what you're actually doing. So I have the standard normal distribution, right, with my z-scores. It's got a mean of 0. And I want to know what's the probability I see negative 2.53 or anything above it, right? So automatically, what does this probability have to be greater than 0.5, right? Because the area to the right of the mean, 0 is 0.5. So the only possible answers here are A and D. Right? And if I'm just guessing, right, what would my z-score have to be for A to be the correct answer? Really close to 0, right? And we might not be comfortable enough with z-scores to know that like -2 is a big z-score. But I mean, I already told you, being 3 standard deviations away, I mean, the probability we're in between 3 above and below is already at like 99.7%. So I mean, once we start seeing z-scores above 2, we're pretty far away from that, right? And so you'd have to have like a z-score of like, I don't know, -0.1 maybe. I don't even know if that's low enough to get that. But, so if I'm, going to guess here, I'm going to go with, D, because it doesn't seem like it's close enough to 0. So sure enough, if I go, this is really small, so just believe it. 2.5, and here's my 3 column. 2.53, it's about 0.9943. Right? So yeah, sure enough, that ends up being, whoops, 0.9943. Any questions on that? Because I know that the table's small for today, but hopefully moving forward, it'll be a little bit easier to follow this. What if I wanted the probability that it's less than negative 2.53? Well, if I just looked up the probability that was greater, what would the probability that's less than that be? Just 1 minus, right? And I did something just now that I should have taken a little more time to do. Sorry. I looked up positive 2.53. I kind of cheated. Why did I know I could look up positive 2.53? Remember, the table always tells me the area to the left. Okay? So when I looked up positive 2.53, the area to the left was 0.9943. And I was acting as though like we should all just know that that's also going to be the probability we're above negative 2.53.
Normal curves are symmetric.
Right, this is symmetric. You can imagine if I had a different color marker. If I were to look up positive 2.53 and get the area to the left here, well, it's really just flipping, right? It's like flipping everything around that mean. It would be the exact same area. They would lay on top of each other exactly. So I kind of cheated there without really telling you. Now you could have also looked up negative 2.53. If you do that, it's going to tell you what, 0.0057. So if you look up negative 2.53 on the table, you'll find the area to the left of negative 2.53 is 0.0057. And if you want the area to the right, you would just subtract that from 1, which sure enough ends up being that 0.9943. So there's multiple ways to kind of do this. I mean, I think probably when we're starting out, don't get fancy like I just did. Just look up that exact value. Look up negative 2.53 in the table, because the table always gives you the area to the left. So then as you're building your picture, you're always thinking about one of the value I see in the table. That's always the area to the left of that value I looked up. But as we start getting more comfortable with it, kind of doing these kind of like little tricks, exploiting the fact that it's symmetric, can make life a little bit easier as well. What we got in time? Okay, so I had like this old data set laying around, and I don't know. Sometimes this is what I do with my free time. So I had found this powerlifting data set, and like it had all these different meets, and it had everyone's height. So like you can kind of see, I just used the height in there, and like it follows this like really nice, I mean, a little rough, right? But it's pretty close to a normal distribution. I also was looking at, I have the data here, yeah, so I'll get to that in a second. So I mentioned earlier, so taking a step away from that powerlifting data for a second, we'll come back to it. Anything with like biological markers or human performance tend to follow normal distribution. So I saw this thing posted on Instagram, this in fact this picture, and they were boasting about like, oh, are you in the 99th percentile for some CrossFit workout? Total reps is like whatever they were doing, how many times they did it, right? And they were like, oh, where are you in the 99th percentile? But the reason I was like really focused on when I saw this, I was like, holy cow, for women, whatever event this is, I mean, I could not draw by hand a more perfect normal distribution. I mean, this thing is like a perfect normal distribution, right? So here's a good example. Like we got a little weird thing going on here with kind of males, but theirs is pretty close as well, right? So, you know, this is a pretty cool graphic because it shows human performance. I mean, CrossFit doesn't have any idea how to create an event that's going to be more normal. I can guarantee you that that's how they're trying to do, right? But just the way that it plays out, human performance follows a normal distribution. What's also really interesting here is that like the variance is pretty close on them as well. Kind of notice we've got a pretty similar height here. And the means, there's not really much of a difference in means there. But anyways, so I got really interested in this idea. I saw that picture. I went out and got this powerlifting data. And if you look at kind of one lift specifically, so I chose the deadlift, and the total kilograms that each one of these lifters lifted. So, I mean, these are a little bit skewed to the right, but I mean, pretty pretty good normal distributions, right? And the only reason they're probably skewed to the right is because people who are really good are going to do a powerlifting meet. People who are really bad probably aren't going to show up, right? So if we actually could have everyone, participate in this lift, we would have a little bit better of a normal distribution. But even so, really, really pretty close to normal distribution. Now, notice like the averages are a little different, right? The mean is about 600 here and maybe 300 kilograms over here. You kind of expect that. But then I've always had this idea that, I still go to the gym, but I used to really be into lifting weights. So I had this idea and like reading all the literature that males and females per pound of body weight, there's no reason, like you can't tell me that one's going to be stronger than the other if they have the exact same amount of muscle mass, right? But the problem is males tend to be heavier on average. I can tell you by looking at this data set, there was a lot more 400 plus pound men in the data than there were 400 plus pound women. Like they're almost non-existent, right? So I can't just look at how much they lifted. I should be factoring in how heavy they were, kind of what weight classes they're in. So there's this thing called the Wilks that you can calculate based off of a lifter's weight and how much weight they lift. So when I calculated this Wilks score for every single lifter, and then I graphed that out, these are, once again, really nice normal distributions, a little right, skew right, because we're kind of missing those people who just don't compete. But here it gets more interesting because now when I look at this Wilks score that factors in body weight, now I look at female Wilks, if I look at the average here, it's going to be 370, a little bit below 400. If I look here, the mean is going to be affected a little bit more by this right tail. But right, the mean here is really kind of right below 400 as well. Those Wilks, so really, when it comes to performance, there's really no differences in gender. In the sense of if you account for that one gender is typically a lower body weight, right? So once you just account for body weight, you already get these distributions looking really, really similar. So I don't know, I thought it was kind of an interesting, on its face, you start playing around with data. I'm sure there's some people who would take this and say, oh, see, guys are way stronger than girls. And you're like, okay, yeah, but they're also like large, like they just weigh more, right? So if we factor in that, yeah, they're like the same. So like what do you want, right? So I don't know. I thought it was a pretty cool example of sometimes, the story you want to tell, like you got to be careful if you're thinking about you have the right variables, if you accounted for the right factors. As we move forward and we get closer to regression, we'll think about how do we account for these things without creating a new variable of Wilks here. How do I just account for things like weight or like height, right? If I was able to somehow factor in height here, I can guarantee the distributions start to look even more similar, right, with that measure. So that is, we'll stop for today. We'll kind of pick back up, work through some examples where we convert a normal distribution to a standard normal distribution, use that table to find different probabilities, and probably do a little bit of Excel work next week as well. So kind of be prepared for that, maybe even on Monday, we'll kind of dive into Excel. Okay? All right, you guys have a good weekend. If I get those back, I will try to get the grades posted as quick as possible.
I have a stand in
Yeah, I'll bring
so they can take
them
pictures
Monday.
So I'll be on the virtual
Oh, the
board.
very just came back to short notice.
I'm just talking to my coworkers, like,
She goes,
they're like, how do a conversation?
probably came at this.
How do I, like, I'm so awkward, like, I'm just like,
You do.
casually talking.
Yeah, they wanted to have a conversation. They should have just not told you that we're reading it.